Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Within the grand edifice of 19th century mathematics, certain documents possess the foundational quality of bedrock, establishing the principles upon which subsequent structures are built. Niels Henrik Abel's monumental work, composed in Paris around 1826 and published posthumously, stands as such a document, while the prompt specifies the year 1844. This likely refers to a later compiled publication of his works, a testament to the paper's enduring importance long after its initial difficult journey from a lost manuscript of the Paris Academy to its eventual recognition. The full title, a memoir on the number of distinct values which a function of a given number of quantities can assume when these quantities are permuted in all possible ways, reveals with precision the scope of its inquiry. This essay will undertake a direct and rigorous evaluation of the memoir's internal claims, proceeding through its logical architecture to assess the arguments, methodologies, and conceptual frameworks as Abel himself presented them. We will explore the work from within, examining the profound machinery of thought that Abel constructed, a machinery that effectively reformulated the central problems of algebra from a search for solutions to an investigation of underlying structure. Section 1, the foundational question, and the permutation framework. Abel's memoir commences with a remarkable clarification of the problem inherited from Lagrange. He considers a general polynomial equation of degree n, with n distinct roots, which he designates x sub 1, x sub 2, and so on, up to x sub n. He then introduces the primary object of his analysis, an arbitrary rational function of these n roots, which he denotes by the Greek letter phi. The central question he poses is deceptively simple if one applies all possible permutations to the n roots within the expression for phi. How many different values will the function assume? This initial framing is a masterstroke of abstraction. Abel moves the focus away from the equation itself and onto the behavior of functions of its roots. The evaluation of this opening claim reveals its power. By making the function phi the protagonist, Abel creates a tool for probing the symmetries inherent in the set of roots. His argument implicitly asserts that all information about the solvability of the original equation is encoded in the combinatorial behavior of such functions. The methodology is purely algebraic and combinatorial. He establishes a universe of n factorial permutations, the full symmetric group on n, letters in modern parlance, and proposes to study the orbit of the function phi under the action of this group. The internal logic is impeccable. A number of distinct values a function can take is a direct consequence of the set of permutations that leave the function unchanged. He has, in these opening paragraphs, established a precise, quantitative measure of a function's symmetry. The claim that this number is a divisor of n factorial is a direct and immediate consequence of this framework, a result that flows with elementary certainty from his definitions, presaging what would become Lagrange's theorem in Group Section 2, the classification of functions by the number of values. Proceeding from his initial framework, Abel advances a series of profound claims regarding the possible values that this number of distinct function values can assume. His most celebrated result from this section is the assertion that for an equation of degree n greater than 4, a function of its roots cannot assume a number of distinct values that is greater than 2 and simultaneously less than n. This is a claim of extraordinary depth, representing a significant barrier in the landscape of algebraic possibilities. The evaluation of his proof for this assertion reveals a masterful command of what can be described as a calculus of permutations. He operates without the formal lexicon of group theory, yet his reasoning embodies its core principles. To demonstrate this claim, Abel effectively analyzes the structure of the symmetric group. His argument proceeds by construction. He demonstrates that if a subgroup of the symmetric group on n letters, for n greater than 4, has an index less than n, its index must be either 1 or 2. He achieves this by showing that any such subgroup must contain all the 3 cycles. The logical coherence of his demonstration is formidable. He constructs specific permutations, composes them, and shows that the permutations leaving a function with, for example, 3, 4, or up to n-1 values unchanged would force the inclusion of all possible permutations, a contradiction. This argument is a stunning piece of pure reason, relying on the combinatorial properties of permutation composition. Its internal validity is absolute. This specific claim about the gap in the possible number of values is a powerful structural theorem about permutation groups, and its placement earlier in the memoir serves to immediately constrain the problem, ruling out a vast swath of hypothetical function behaviors for higher-degree polynomials. Section 3 functions sharing a common symmetry. Abel next introduces a concept that powerfully illuminates the relationship between different functions of the same set of roots. He puts forth the proposition that if two distinct functions of the roots, let us call them phi and psi, possess the identical set of values under all n factorial permutations of the roots, then one function can be expressed as a rational function of the other. In the language of a later era, if two functions share the same stabilizer subgroup while in the symmetric group, they belong to the same field extension of the base field of symmetric functions. Abel's claim is a statement about algebraic dependency. His proof for this involves a brilliant use of symmetric polynomials. He constructs a new function, let us say capital theta, involving both phi and psi, in such a way that it becomes symmetric with respect to the roots. Since any symmetric rational function of the roots can be expressed rationally in terms of the elementary symmetric polynomials, which are the coefficients of the original equation, this function theta can be considered a known quantity. From the equation relating phi, psi, and theta, he then demonstrates that psi can be isolated and expressed as a rational combination of phi and the equation's coefficients. The evaluation of this claim highlights Abel's deep understanding of field theory. Decades before the concept was formalized, he intuits that functions with the same symmetry profile are, in a profound sense, algebraically equivalent. This section of the memoir is pivotal because it establishes a form of equivalence class. It asserts that the study of a single function, phi, and its number of values, is sufficient to understand the entire family of functions that behave identically under permutation. This is an argument for efficiency and structure, showing that the combinatorial property of having a certain number of values corresponds directly to a specific algebraic relationship. Section 4. The critical case of two-valued functions. The memoir dedicates specific and rigorous attention to the special case of functions that assume precisely two distinct values when the roots are permuted. Abel's central claim in this part is that any such function can be expressed in a particular algebraic form. Specifically, he demonstrates that such a function, which we can call phi, must satisfy a quadratic equation whose coefficients are rational functions of the coefficients of the original polynomial. The form he derives is phi equals p plus q times the square root of delta, where p and q are symmetric functions of the roots, and delta is the discriminant of the original equation. The evaluation of this argument reveals its direct and powerful connection to the theory of equations. The discriminant, by its very definition, is a function of the roots whose square root changes sign under any odd permutation, thereby yielding exactly two values. Abel's claim is that any function with this two-valued property must be structurally linked to the discriminant. His proof is constructive and elegant. He shows that the sum of the two possible values of phi is a symmetric function, as is their product. These symmetric functions are therefore expressible in terms of the original equation's coefficients. This means that the two values of phi are the two roots of a specific quadratic equation whose coefficients are known. The solution of this quadratic immediately yields the expression involving the square root of its own discriminant, which he then shows is rationally related to the main equation's discriminant. This section is a crystalline example of Abel's method. He takes a combinatorial property, a function having two values, and proves that it necessitates a specific algebraic structure, the presence of a square root, This provides a tangible link between the abstract permutation framework and the concrete process of solving equations. Radicals. Section 5. The concept of the irreducible equation. Abel introduces a subtle but crucial concept for the coherence of his entire project, a notion. He terms the irreducible equation, which is analogous to the modern idea of a primitive group action. He posits that for his general analysis to hold, the equation under consideration must be of a type where it is impossible to express its roots in terms of the roots of an equation of lower degree. More specifically, he considers the group of permutations that leave all rational relations between the roots invariant. He claims that for a truly general equation, this group will be the full symmetric group. He then considers equations where this group is smaller, yet still possesses a property he intuits as primitivity. The roots cannot be partitioned into smaller sets, or blocks, that are merely shuffled amongst themselves by the permutations in the group. The evaluation of this conceptual move shows its strategic necessity. Abel recognized that if the roots could be so partitioned, the problem would decompose into simpler problems of a lower degree. His insistence on this property of irreducibility, or primitivity, ensures that he is always dealing with the most complex combinatorial case. This claim is less a theorem, to be proven, and more a foundational assumption, that defines the scope of his inquiry. By delineating this class of equations, he sharpens his analytical tools, ensuring they are applied to the core difficulty of the general polynomial. It is a testament to his intellectual foresight that he identified this property as being central to the problem of solvability, a concept that Galois would later place at the very heart of his own theory through the formal definition of primitive and imprimitive groups. This section fortifies his argument by specifying the precise nature of the algebraic object he is dissecting. Section 6. Abel's theorem and the solvability criterion. The intellectual climax of the memoir is the presentation of what is now known as a version of Abel's theorem on the solvability of equations. He puts forward a monumental claim: if a general equation is solvable by radicals, then the group of the equation, the set of permutations of the roots that preserves all their algebraic relations, must possess a very special property. While he does not use the term solvable group, he describes its functional equivalent. He argues that if the solution involves a nested series of radicals, this implies that one can construct a corresponding tower of functions of the roots, each assuming a prime number of values relative to the previous function in the sequence. He claims that for a solvable equation, one can always find a function of the roots, let's call it v, such that all the roots of the equation can be expressed as a rational function of this one quantity, v. Furthermore, the equation which v satisfies must itself be of a particular, simpler form. The evaluation of this section reveals it as the grand synthesis of all the preceding parts. The argument is intricate and relies on reversing the logic. Instead of starting with an equation and looking for a solution, he starts with the assumed form of a solution, a nested tower of radical extensions, and deduces the necessary consequences for the permutation properties of the roots. His proof involves a delicate analysis of how adjoining a radical, such as the pth root of some quantity r, affects the group of admissible permutations. He shows that this action partitions the permutations into cycles of length p. This argument, while dense, is logically watertight. It forges an unbreakable link between the algebraic structure of the solution and the combinatorial structure of the permutation group associated with the equation. It is this claim that ultimately forms the basis for the impossibility proof of the quintic, for it establishes a structural test that the general quintic equation fails to meet. Section 7. The transformative power of commutative permutations. In a final stroke of genius, Abel investigates a spatial class of solvable equations, and in doing so, introduces a concept that would bear his name for all time. He examines the case where the permutations involved in the tower of solvability possess the property of commutativity, that is, for any two such permutations, which we may call S and T. Applying S then T to the roots yields the exact same result as applying T then S. His claim is that if the permutations associated with the adjunction of new radicals to the solution all commute with one another, the equation is not merely solvable, but solvable in a particularly elegant way. He demonstrates that in such a case, the roots of the equation can all be expressed explicitly using a formula that involves the roots of unity. The evaluation of this insight is that it represents a discovery of the first magnitude. Abel isolated the property of commutativity as a key feature that simplifies algebraic complexity. He was the first to understand that commutativity in the permutation group corresponds to a specific and simpler form of the algebraic solution. This section of the memoir is less about the general problem and more a deep dive into a particularly well-behaved subclass of problems. His analysis here gave birth to the entire field of Abelian equations and, by extension, Abelian groups and Abelian varieties. The claim is profoundly constructive. He provides the explicit form of the solutions for these equations, showing how the roots are interrelated through multiplication by roots of unity. It is a moment of pure conceptual beauty, where a simple, abstract algebraic property, commutativity, is shown to have dramatic and concrete consequences for the explicit construction of solutions. This was a new kind of mathematical analysis, one focused on identifying and exploiting deep structural properties. In conclusion, a meticulous evaluation of the internal claims of Abel's 2826 memoir reveals a work of almost unparalleled logical cohesion and conceptual foresight. The document is far more than a precursor to Galois theory. It is a complete and self-contained intellectual system that fundamentally reshaped the understanding of algebraic equations. From its initial, clear-sighted framing of the central problem to its final, brilliant isolation of commutativity, each section builds upon the last with inexorable logic. Abel's claims about the possible number of values for a function of roots, the algebraic dependency of functions with shared symmetries, the specific form of two-valued functions, and the structural constraints imposed by a solution in radicals are all rigorously argued and internally sound. The memoir's genius lies in its methodology. Abel effectively invented a new way of thinking about algebra, transforming the problem from a hunt for a formula into a precise science of structure. He demonstrated, claim by powerful claim, that the secrets of an equation were held not in its coefficients, but in the symmetries of its roots. The work stands as a testament to the power of pure reason to uncover the hidden architecture of the mathematical world, providing a definitive and enduring foundation for the entire subsequent development of modern algebra.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.